In most countries, roughly 2/3 of people earn less than the average wage. That sounds like it can't be right. If it's the average, shouldn't about half be above and half below? No. And the reason isn't a trick or a measurement problem. It's that the mean and the middle are different things, and they only coincide when the distribution is symmetric. Income isn't symmetric. Almost nothing interesting is. Today, the difference between the mean and the median and when to trust what a log-normal distribution is and why it shows up in incomes and file sizes and city populations, heavy tails, and why they break the tools from episode 4, and one transformation that makes a lot of this tractable again. Let's be precise about the two words. The mean is the total divided by the count. The median is the value in the middle when you sort everyone. For a symmetric distribution, they're the same number. For a right-skewed one, the mean gets dragged upward by the long tail, while the median just stays where the bulk of the people are. The gap between them is a direct measure of how skewed your data is. Here's the thing that makes it concrete and slightly alarming. Take a room of 100 ordinary people and compute the mean income. Now, one billionaire walks in. The mean income of the room jumps by roughly 10 million pounds a year. The median moves by essentially nothing, one position along the sorted list. One data point moved the mean by more than the entire room earns. Any statistic that a single observation can dominate is fragile by construction. The distribution that generates this behavior is the log normal, and it has an elegant definition. A quantity is log normal if its logarithm is normally distributed, which means the underlying thing isn't produced by adding lots of small effects. It's produced by multiplying them. Growth rates, compounding, proportional changes. Anything where the effect is a percentage rather than an amount tends to land here. So compare the two generating processes directly, because this is the whole episode in one idea. Add lots of small random effects, and you get a normal distribution. That was the central limit theorem in episode 5. Multiply lots of small random effects, and you get a log normal. Addition gives you the bell. Multiplication gives you the long right tail. Same ingredients, different operator, completely different world. Let's generate 100,000 log normal values and look at the summary numbers. The mean comes out at 1.65, the median at 1.00. The mean is 65% higher than the median, and that gap exists even though nothing anomalous happened. That's just the shape. If someone hands you a mean without a median for data like this, they've told you very little. Here's what it looks like. Piled up on the left, a long tail stretching right, and the tail keeps going well past where the histogram becomes too sparse to see. The two lines mark the median and the mean, and notice they're in visibly different places, with the mean sitting out where relatively few observations actually are. Now watch what happens when we take the logarithm of every value. A bell curve. That's the definition, made visible. Which brings us to the practical consequence, and it connects back to episode 4. In a normal distribution, sample means converge quickly and outliers are genuinely rare. In a heavy-tailed one, the sample mean is unstable. It jumps every time a large value happens to appear, and it can keep jumping no matter how much data you collect. Here's a running average of log normal data with a heavy tail. It doesn't settle. It keeps getting jolted. So, a checklist. Report the median alongside the mean for anything skewed, and report percentiles rather than standard deviations. Consider working with the log of the values, which often makes the analysis behave. Be suspicious of any average where a single record could move it noticeably. And plot the histogram before you summarize, which is the same advice as episode 4, because it is genuinely the highest value 10 seconds in applied statistics. The honest caveat: log transforms only work on strictly positive data, so any zero breaks it, and the common fix of adding 1 is a real choice with real consequences, not a free move. And be careful about what you're claiming. The average of the logs is not the log of the average. If you transform, compute, and then transform back, you get the geometric mean, which is a different and usually smaller quantity than the arithmetic mean you started with. One sentence. When effects multiply rather than add, the mean stops describing anybody, and the median plus a few percentiles tells the honest story. Next episode, the most misused number in all statistics. Correlation. In a simulation showing how easy it is to find a strong one in data that is nothing but noise.